Welcome back to Part 7 of Section 1.1, Displaying Distributions with Graphs. Last time we looked at the different types of shapes, not all of them, but some of the different shapes distributions could take on. Now we're just going to summarize organizing our quantitative data. Now quantitative data can be organized in many ways, many different ways. We're going to look at these histograms that are based on data values. They're good for discrete data. The one that you see on the left. And remember, this is the example of those arrival times at Wendy's. And as you note, labels are in the middle of the bars at the midpoint, because each of those bars represent a specific value. Now, histograms are great when we have continuous data too. However, the bars, when you look at them, they're intervals of values. So you'll see the cut points that are at the ends of the bars on the histogram. So they're in between the bars, and that just shows us that each of those bars represents a range of data value, where the left endpoint is part of that bar, but the right endpoint is not. The right endpoint begins the data values for the next bar. So in that first one, 0 to 2, 2 is not included in there. So we would say we see the values of 0 to 2, not including 2 times. We see the values of 2 to 4, not including 4. We see that 5 times. Now the shape of the distribution describes a variable. Histograms are very useful for identifying the shapes. But remember, the histogram is not unique. Depending on the range that we use, the number of classes that we use, can change the shape of the histogram. So that's why we try to get the right number of bars. We need between 5 and 20 bars is usually a good rule of thumb. And generally the number of bars we want to use is somewhere near the square root of the sample size. It's a good general rule of thumb. And we try to get a number that has factors so that we can have bars between 5 and 20. Now we're going to talk about time plots. Time plots, again, is an extremely useful view of what's going on with the data. It tells us the value as time goes on. So a time plot shows behavior over time. Time is always on the horizontal axis, and the variable being measured is on the vertical axis. This allows us to look for an overall pattern or a trend, and deviations from that trend. Connecting the data points by lines may emphasize this trend. Look for patterns that repeat as known regular intervals or seasonal variations. Time series data. It's a variable is measured at different points in time. Time series plot. A time series data, a vertical axis plotted against time, the horizontal axis. Lines are drawn connecting the points. We can identify long-term trends and identify regular occurring patterns with time. So we can see from August 3rd all the way to January 4th, there's a steady upward trend. Now we could say from June 04 to September 04, there's a general downward trend. There is no regular seasonal pattern that we can see here, but we can see in little intervals of times, upward and lower trends, upward and downward trends. And looking at this, you can see there's lots of ups and downs, but generally it would increase, but you did have some downward trends in there, but there is no pattern that we see in this. A comparative box plot is very nice. This is the average tuition, public versus private. And we can see that both public and private have an upward trend in there, but the public is very, very minimal. The slope of that one is very small. The private took a huge increase from 1980 to the year 2000. Just a huge upward trend there. Now, a very important concept is outliers. They're extreme values that fall outside the overall pattern of a distribution. We always have to look for outliers and try to explain them. If we can't, we have to be very careful in the type of analysis we do. Now, when an outlier occurs because of an error in recording or measuring, we can wipe our brows with a sigh of relief because that's just input error or recording error, and we can knock out that data point. However, if it occurs naturally or the observational unit may be fundamentally different, that's where the trouble comes in, and how we do our analysis is very important, because there are some analysis that if you have an outlier, it greatly disturbs that analysis. In other words, it makes it unreliable if you use it. So if someone just willy-nilly gets rid of an outlier, does the analysis, their analysis, although they get a number and they can make a conclusion, the conclusion is not reliable. Now in this example, you see the overall pattern is basically symmetric, except you see Alaska and Florida have unusual representations of the elderly in their population. A large gap in the distribution is typically a sign of an outlier. And that concludes section 1.1. Thank you.